Hello everyone and welcome to FusionEPtalks, a student-led webinar platform for sharing knowledge about nuclear fusion, science and engineering. I am Jose and I would like to introduce our speaker today, Guangming Zhou, and he's going to talk us about the breathing blankets of demo. His talk is going to be about the status of the HCPB, that is the Helium Cooled Pebble Bed, is one kind of breathing blanket, and the status of the design and research and development activities in this kind of breathing blanket. Without further delay, I give the floor to Guangming.
Thank you, Jose, for inviting me to give this talk about the Helium Cooled Pebble Bed breathing blanket for the European demo. My name is Guangming Zhou. I'm the lead engineer of the HCPB blanket, and this talk is prepared together with Francisco Hernandez, who is the former lead engineer of the HCPB blanket. So I will first to introduce why we need breathing blanket, and then I will say some word about what is HCPB breathing blanket, and then I will say some word about the top level requirements. Thereafter, we'll focus on the current HCPB breathing blanket. So after that, I will outline the outstanding challenges that are facing us and the prospective solutions to tackle these challenges, and then I will conclude. First, before going into detail, I will first say some words about the role of the tritium. Here in this picture, we can see a schematic of a fusion power plant of T reaction. In the reactor core, we have the plasma, and in the plasma there is the DT fusion. This DT fusion will react to produce neutrons and helium together with energy, and these neutrons will go heating the wall, so-called plasma chamber wall, which is the breathing blanket and the diverter. And the neutrons will react with the material that is in the blanket to produce tritium and heat. The tritium will be extracted through our procedure and prepared in the tritium plant. And then thereafter, they will be rejected into the reactor. The heat, on the other hand, will be transmitted through coolant to the power conversion system and will be used to generate electricity. We know that the deuterium is very abundant. It can be harvested from the seawater. However, the tritium, which is a reactive element, has a very short lifetime. It decays at a rate of 5.5% per year. And for each gigawatt fusion power device, we will need for each 4 per year about 56 kilogram tritium. For EU demo, we are a 2 gigawatts fusion power device. We will need for each 4 per year about 112 kilogram tritium. And looking into the global inventory of tritium, we can see here the maximum, the peak will be reached in 2030, and the maximum inventory is less than 40 kilograms. Therefore, we need to produce tritium in situ. And that's why we need the tritium breeding blanket. And the tritium breeding blanket has 3 main functions, along with the tritium breeding. For the tritium self-sufficiency, we will have also the function of heat for the electricity production, and the to contribute to the shielding, protect the superconductors from the neutrons. Here is a picture of the reactor. As we can see here, the core, of course, is a DT plasma, and the neutrons will react with the material in blanket, which is the lithium-6. And this neutron will, through this reaction, will generate tritium, and this tritium will be regenerated into the reactor. And behind this blanket, we have the vacuum vessel, and behind the vacuum vessel, we have the superconductor. So the function of blanket has also to protect the magnets from the nuclear irradiation. Some words about the Eurofusion program. In Europe, the Eurofusion is coordinate all the European efforts in developing fusion energy. And the Eurofusion is a consortium consisted of 30 research institutes plus 150 affiliated universities from 28 countries. Totally, we have more than 4,000 scientists and engineers. We have a good budget. From the last 7 years, we have 1.2 billion euro. And from 2021 to 2025, we will have 1 billion euro for the whole Eurofusion activity. This is on the left side is the organization chart. It is managed by the program manager, who is currently Professor Toledone, and under his direction, there are 3 department: the fusion science department, fusion technology department, and the administration department. The demo activity, the demo program is under the fusion technology department, and in the demo program we have breed blanket project, magnets project, balance of plant project, and etc. And the blanket is one of the 12 work packages, and it has also a lot of interface. For example, with the work package material for the rules and the material, the Eurofer and tungsten. For the balance of plant, we will have interaction with the coolant supplying and feeding out. With the remote maintenance work package, we have also interface to know how the blanket can be remote maintained, and also the safety and the environment work package, which is very important because the breeding blanket is a very sensitive component which will produce tritium, and of course it's a nuclear component, pressurized. And also with the tritium fueling and vacuum, here is because we are produce tritium, we will have a lot of interface with the tritium fueling and vacuum work package. Another work package is the heating and current drive, because they will cut out the breeding blankets. in order to heat and drive the plasma. So we also have an interface here. And this DC, this is so-called diagnostics and the control work package. Again, because this diagnostic need to diagnose the plasma, facing the plasma. So we will also have interface with them. A few words about the HCPB breed blanket in the breed blanket work package. The breed blanket work package is has a lot of participants. It is led by KIT, the Karlsruhe Institute of Technology in Germany, and together with Demo Central team. Under this work package, under the leadership of the project leader, we have 4 leader engineers for different areas for the HCPB breed blanket, HCPB tritium extraction and removal, and the WCLL breed blankets, and the WCLL tritium and the removal system. Today here, I'm talking about the tritium breed blanket, the HCPB tritium breed blanket. It is organized like this. It is consists of the system design and modeling, which will be focused on the design activity, design and analysis activity, and the design supporting analysis activity, and the technology R&D activity, which will be focused on the solid breeder development, neutral multiplier development, helium cooling, and manufacturing, and the first wall coating with tungsten, and last but not least, the prototypical mock-up testing. So what is a HCPB breed blanket? The HCPB breed blanket is the so-called Helium Cooled Pebble Bed breed blanket. We are using helium, pressurized helium as coolant, and for the tritium breeding, we are using lithium ceramics, which is a solid material in a form of pebble bed. That's why it's called pebble bed. And for the neutron multiplier, we are using beryllium. In this case, in current design, we are using berylite as a neutron multiplier. This is needed because as you may know that the materials in the blanket structure were not only react with lithium, it will also react with other material which will absorb and absorb the neutrons, which is not good. We need to, therefore, we need this neutron multiplier to multiply neutrons in order to have enough neutrons to react with lithium-6 to produce enough tritium. And this tritium is, of course, the fuel of the DT fusion plasma. For the structure material, we are using the reference material, the urethane. And for the heat extraction, as I said, the coolant is the pressurized helium at a temperature between 300 degrees C to 520 degrees C. Regarding to the top level requirements, we need to obtain a reactor availability more than 30%. We need to fulfill the tritium breeding ratio of greater than 1.05. When we are designing it without consider the loss of coverage, we need to have a TBR of greater than 1.15. And the requirement of shielding, nuclear shielding, need to protect the colloidal field coil to limit the nuclear heating to less than 50 watt per square meter. For the vacuum vessel, we need also to limit the damage, the radiation damage due to neutrons to less than 0.2 dPa per 4 per year. And also for the structure that is needed to be rewired, we need to limit the helium production in the structure. It should be less than 1 APM per 4 per year. And also the temperature limits for the Eurofoil, we need to make sure the temperature is between this range. The lower bound is determined by the PBDT, the so-called back-to-operator transition temperature. That is, the temperature should be higher than 350. And the up limit is limited by the creep of the Eurofoil. Higher than this value, the creep stress will be very low. And also we need to fulfill the criteria that is defined in the nuclear codes and the standards. For example, the ASME, the RCCMX in France. At the moment, we are using the RCCMX as the reference code. Of course, in the Eurofusion program, we have also a code which is under development, the so-called demo design code for in-vessel components, which is under development in the work package material. We need to fulfill all the stress limits and the design of the components and the manufacturing and the joining qualifications should also follow the rules that is defined in the codes. Regarding to the tokamak baseline of the EU demo, currently we have the baseline 2017 with a major radius of about 9 meters and a minor radius of about 3 meters with a fusion power of about 2 gigawatts. The tokamak is divided in different sectors. Totally, for the current design, we have 16 sectors, and therefore the blanket is also divided into such a manner. In each blanket sector is composed of 5 blanket segments, 2 inboard segments, and 3 outboard segments, as you can see here. The right inboard, left inboard, left outboard, central outboard, and the right outboard. And all of the cooling pipes and the tritium extraction pipes will go through the upper board through the vacuum vessel upper board, as you can see here. So the current design activity of HCPB, here you can see a detailed view. At the front is the so-called first wall. Behind the first wall is the so-called breeder zone, which composed of different materials: the neutron multiplier, the tritium breeder, and the structure materials. It's a detailed view. And the coolant is going from the inner tube, and then it will return from the annular cap and connected through this space, and through here it will be routed to the outlet manifold. In this so-called PIN, we have this so-called cladding. In the cladding, we have the ceramic breeder for the tritium breeding. And this pin is inserted into the pressure tube. And this pressure tube is again inserted to the beryllium titanate block, which is the neutron multiplier material. The coolant scheme is from left. We can see here the scheme. The coolant is coming from the primary heat transfer system. It will distribute along the manifold in the behind. It's actually here at the behind. And then it will distribute to the first wall. And after cool the first wall, it will be connected to another manifold. And through this manifold, it will be distributed to a breeder zone. And the detailed schematic is shown here. So you can see it is cooled first in a counter flow manner and connected at this manifold, and this manifold will distribute to different pins, which is the breeder zone, and it will return back and to the outlet manifold with a temperature of about 520 degrees. The design analysis we need to do before any design can be considered consolidated. First, we need to do the nuclear analysis. We are using a fully heterogeneous MCMP model, and with this current design, we have achieved a very good PR of 1.2. And the neutron shielding is also fulfilled the requirement. We found that the dPa of the vacuum vessel is 0.13, which is fulfilling the requirement. We found also different shielding materials, for example, the boron carbide and the different hydrides and the tungsten carbide. And due to the property, for example, the weight, the density, we found that we prefer this boron carbide as a shielding material. Through the nuclear analysis, we can also get the nuclear heating data, which is needed as input for the thermohydronics analysis. Here is showing a detailed local analysis, which is only a slice of the blanket. It's a cutout from here. And we found that the temperature, after several design iterations, we fulfill the temperature limits of different materials. And this temperature field is also a further input for the thermomechanical analysis, as shown here. We need to calculate, taking into account the pressure, the temperature field, and the EM node, the electromagnetic nodes, the weight into account. And here we do the stress assessment and follow the ICCMRX rules. Furthermore, we have done also a global thermohydronic analysis and the thermomechanical and thermomechanical analysis. We did, this is a very innovative way we have developed at KIT, especially when it comes to a very big model. We are using the porous media method to get an equivalent pressure loss. Using this, we can simplify the model and at the same time, we keep the results as close as to the real geometry. We from this analysis we can obtain the pressure drop. We can obtain the mass flow distribution, which is important for cool down the blanket. For the design supporting analysis, we have planned the tritium transport analysis at system level, which is done together with CMAT in Spain. And we at the KIT we also developed a new tool, a 3D tool based on OpenFlow. This is a picture of the Philippine tritium transport. Regarding to the pebble bed mechanical analysis, we at KIT we developed an in-house code which is based on the discrete element method, and together with University of Turin, they have developed the in-house code to simulate the Helium flow modeling, which is a very effective tool in order to get a very quick feedback to the design. For the technology R&D, solid braid development at the KIT, we have developed the so-called Karlsruhe process, the Karlsruhe lithium silicate process. We have updated this facility using this Karlsruhe process, and this pebble bed, this solid braid is in form of a pebble bed. It will be, it is produced in KIT and will be characterized, will be further irradiated in the reactor, and thereafter there will be the post-irradiation examination also to be done at KIT. Regarding to the neutron multiplier development, we have to say that this activity started at a later stage. Actually, we started this activity at around 2018, and this block, as you can see here, this is hexagonal block with a central hole together with our industry partner. And this technology has also won the innovation prize of SOFT. This block also not only being produced, characterized, and it has also been tested in the furnace. Currently, we have already tested more than 200 thermocycles to see the effect on the block. For the helium cooling technology, we know that the plasma freezing component will receive a very high heat flux. It's about 1.2 megawatt per square meter. We need to use ribs in order to enhance the heat transfer performance. In the past, we developed different configurations using, for example, this straight one and this field one. This is the V-rib. We are using large AD simulation in CFD to calculate the performance. And after that, we select the V-rib configuration because it has the best performance regarding the heat transfer enhancement and the pressure drop. After that, we test this technology in our lab, and the result is already published. We are going to further develop this technology to test it up to 1 megawatt per square meter heat flux. Regarding to the first wall manufacturing, at KIT we have also developed a technology which is also patented. This advanced technology is a combined technology of using conventional manufacturing and additive manufacturing to manufacture the tritium promoter, that is the V-ribs. The V-ribs assumed together with our industry partners. Here shows the different steps. The first step is to cut the shape and manufacture this V-rib, and then we fill it with filler material, and then we machine of it, and then we apply the cold spray, the active manufacturing procedure. After that, we rinse the filler material and then machine out the left part. After that, we add a cover plate, and after this step, we will heat it using heat to weld this cover plate together with the structure below. And with this technology, we are able to demonstrate that the additive manufacturing technology is not considered as a pressure vessel, pressure inbox welds. As we can see here, after that, of course we need to check the property of the welding, the heat. We can see here, we found that the Sharpie test, and we see the property is comparable with the normal urethane material. Regarding to the coating, the coating of the first wall with tungsten layer is very important for the protection of the blanket and also to minimize the wall erosion. However, the tungsten and the urethane has a different thermal expansion coefficient. We need to mitigate this, otherwise the tungsten will be cracked and will be not contact with the coating will be not there anymore. So the technology that we're using is the functionally graded material, which means here the steel substrate, and then we have different percentage of tungsten, layer by layer, and then in the end we reach 100% of tungsten. This technology has developed at the KIT from the lab scale, and we transfer this technology to industry. And this is also tested at KIT in the helium. Up to now, we are doing the testing on the flat top. We will further continue the activity with a curved surfaces, because at the first wall we have a bending, which also need to be coated. This is further activities. For the prototype typical mock-up testing, as for now, we have designed a mock-up of the HCPB breed blanket, the fuel pin concept, and this is a very very challenging work, as this is a pressurized component with high temperature and high pressure at temperature of 300 degrees C at the pressure of 8 megapascal. Before the design can be finalized, we need to send the design to the notified body to examine the design and to get certified. After that, we can then manufacture the component. After the manufacturing, we need to again to test, to pressure test the component, and after that we assemble it to the facility, assemble different parts together. This is a large component. It's about 2 meters high, and after the assembly, we then integrate the mockup into the helium cooling loop. The helium is helium loop Karlsruhe. We have finished also the first runs at the end of April. We will present the results in the next soft, which will be taking place September this year. Okay, even though we have obtained a lot of progresses, we still need to face a lot of challenges. The first one is the running, the reliability, availability, integrity, and the maintainability. As you know that the blanket is very complex, we will need to manufacture it. We need a lot of wheels, and the wheels that under real fusion conditions, these wheels are prone to fail, which means the reliability of the component is very low. And in order to solve this issue, our proposal is to solve this issue by design, to propose a new concept. We called it a fault-tolerant HCPB concept. Second challenge is the limit heat flux capability. We have a limit of about 1 to 1.5 megawatt per square meter. Higher than this one, we cannot handle it. One of the strongest limit factor is the urethane, because it has a limited thermal conductivity. Of course, if we can develop a very good material which has all thermal conductivity like copper or the copper chrome zirconium, then we can solve this issue. However, we cannot develop such a magic steel. So we need to rely on limiters to take the heat flux, to take the high heat flux. And the third challenging is the low reliability of the tritium modeling, because at the moment we have a lot of uncertainties, the parameters that is used in the modeling. So in the future, we need to cross benchmark with other tools, or better, we need to benchmark with experiment. And the fourth challenge is the tritium permeation to coolant, which can lead to safety issues. Because tritium is like hydrogen, is permeate at very easily at high temperature. It's like permeate through, for example, the steels at high temperature very easily to the from one space to another space into the coolant, which is a safety issue. So we need to think of a new scheme to reduce the tritium formation. For example, for HCPB, we are proposing to using another kind of tritium extraction project gas. We plan to add steam to the project gas. In this way, we can oxidize the tritium into H2O, and the H2O is not permeable. In this way, we can reduce the tritium formation in coolant. The fifth challenging is the steel embrittlement. When the temperature is lower than 550 degrees and under irradiation conditions, there will be ODBDT shift. We need to avoid this. So we increase the inlet temperature of the coolant, or we use less coolant to keep the temperature of steel high. Regarding to the manufacturing, which is one of the most challenging one, especially for the urethane, because the urethane is another commercial or valuable steel, which is developed specifically for the fusion reactor in Europe. The manufacturing and welding is very challenging, and the technology release, the costs are very high. The technology release is low, and the cost is very high. We need to, when possible, we need to develop advanced manufacturing in order to increase the release level and maybe also to reduce the cost. Regarding to the lithium-6 enrichment, as you know that in the blanket we need to enrich the lithium-6, because in nature we have only a few % of lithium-6 in nature. Most of them are lithium-7. However, we need lithium-6 to react with neutrons to produce tritium, and therefore the enrichment is needed. This the cost of enrichment is also uncertain. We need to, and it cannot be solved with the market package of a breed blanket. So we decided to promote this risk to a higher level, to demo level. Regarding to the low release of the available design codes, and this is of course also dependent on the progress with work package material. We need to actively interact with the code developers, and to until then we can improve the release. Regarding to the tungsten coating, as you know that we are doing some lab scale mockup and semi-industrial levels mockup. We are not yet ready for demo scale, which is very large. It's about 1 meter wide, 2 meter high, and at the moment this is not yet it's not yet finished. We need to continue to develop this technology. So here coming to the conclusion, I have talked about the HCPB main characteristics, the challenges, and as you know, we have a lot of challenges. There are a lot of interesting topics to be investigated, and we have a lot of, therefore we have a lot of topics for master and doctoral thesis. And feel free to contact me and at this email address. With this, thank you for your attention and open for questions, comments.
Thank you very much, Guangming. So now for the questions, if you have any, please raise the hand. You can find the option in reactions, and I can give you the word if you have any questions. Okay, we have one. Let me see.
There is one from Amelo.
Yeah, okay.
Yes.
Hi,
yes.
Amelo.
Hi, Guangming. Thank you very much for this very, very interesting talk. And thanks also for FusionEP for organizing this really interesting talk. I mean, probably I know most of this information because we worked together before on the breathing blanket. But I was just interested to know how much is the HCPB concept is advanced for being selected for demo eventually. So I think there are two concepts now, which is HCPB and WCLL. So I want to know what are the chances or the probability that HCPB is finally selected as the baseline blanket for demo. If there is information on this, please.
It's a good question. Actually, at the moment we cannot say anything about that. From both blankets, we have advantages and we have also drawbacks regarding of the material that is used, regarding of the structure, I mean the configuration that is used. We cannot simply say which one is better, which one is better to be the driver blanket. We need until 2024. At that time, we will have the blanket selection activity. It will be done not by us, it will be done by external panels from the community.
Okay, thank you very much.
Thank you.
Maybe also just another question, if you allow me. For the development of the blanket, are you still using the baseline of 2017?
Yes, exactly. This is the latest baseline that we are have in the Eurofusion demo program.
Okay, thanks.
Okay, we have another one. It's from Chuan Ren Wu.
Hi, yeah. Okay, yes, thank you for the moderator. So I'm also from KIT, so I know Guangming also from his office. I think I have a lot of questions, but I think it's better to go to your office and ask you. But here I have some specific questions for, about the slides and about design. That's very interesting. And could you show your slides again?
Yeah.
So to be honest, I know.
Which slides?
So if you could go to 16, to just a very curious question. So because I know nothing about blankets mostly. So like this simulation so this slide simulation. So it is very interesting to me because for my intuition, I would design such things like symmetric, but it looks not very symmetric. Is there any special reason? Because if this
it's a good question. Of course, you're right. You're totally right. And I will show you why it is not symmetric. For the inboard and for the inboard, it can be designed symmetric. For the central outboard, it can also be designed symmetric. But for the lateral, for the right outboard and the left outboard, it cannot be symmetric because of this tower's configuration. We cannot, it's simply like that. And also, as you can see here, the shape. When you go from the top to the equatorial region, the blanket, the toroidal sides, the toroidal sides will automatically be greater than the region here.
Yeah, okay, I see. It makes sense.
Yeah, otherwise, yeah, we cannot do anything otherwise.
Okay, may I ask another question if you go to slide 20?
20.
I didn't understand here is why you do these ribs or the grooves vertical to the pipe. If you like cooling, then it should be somehow parallel to the pipe. Do you understand my point?
You mean, yes, maybe it's not so clear. Here you see the ribs here. Actually, the plasma is from this side. It will be, what do you mean, parallel to the heat flux?
Okay, I mean into the tube, the grooves. Not
the heat flux is like this. It will be parallel to this pipe, and then the flow is from here.
Yeah, I mean the flow. I mean the flow. If you like to cool this flow, to my intuition, it should be along the flow direction, not perpendicular.
No. In this way, the flow is from this direction. It will promote turbulence in this surface after the ribs.
So you like this turbulence to mix the coolant, or okay?
Yeah. We need to promote the turbulence in order to have a better heat transfer.
Okay. Okay, I think I understand that. Yeah, thank you. The other questions I can come to you and ask. I think I have a lot of questions. Yeah, thank you.
And we have another question from Amro. Okay, you can.
Yeah. Yes, thank you. Just one last question for Guangming. You say there are opportunities to make PhD related to the design of the blanket presently at KIT.
Yes.
Okay. Are the positions already open or ready for applicants?
No, not yet. We have a lot of topics at hand, but we need to select one or two to do. I can give some information. Okay, I will share my screen for this. For the pebble bed mechanical analysis, we need to develop a tool that will be able to model the behavior of the pebbles. This is one topic. And another topic is the testing, the mock-up testing, the qualification of the component that we developed.
Okay, but so you are not accepting applications at the moment?
Not yet. If you are interested, just keep informed at KIT at this website.
Okay, thank you.
Thank you.
Okay, thank you. I think we have not more questions. Okay, so very interesting talk, Guangming. Thank you very much.
Thank you.
We see we have a lot of things to do, but it's nice to have a plan and see how it's going. And very good luck. We hope we will see good results soon.
Thank you. Thank you for the invitation.